Hey guys, so in this video, I'll be showing you in benzene substituents, you have these groups here, NO2, aldehyde, nitrile, a ketone. Why are these groups electron withdrawing, deactivating, and meta-directing? Right, so I'm going to prove to you. So let's start with NO2, a nitrobenzene. Now for this proof, in the benzene ring, we have to show the alternating double bond in order to show the mechanism. How do we draw NO2? It's a nitrogen connected to the benzene ring, double bond to the oxygen. The other side is a dative bond to the other oxygen atom. As you see, electron flow within the ring, the pi electrons, and here we have what we call the conjugated double bond. We have pi bond, then the next bond, there's no pi bond, but the following bond, there is a pi bond. So it's alternating, pi without pi, pi bond. This means that electrons could also flow out of this benzene ring. So I can do this arrow pushing. Electron pair going to the next bond. And we know that nitrogen cannot take more than 8 electrons because it's coming from period 2 of the periodic table. That means this pi bond could give way and push it here. So eventually, since we are drawing resonance structure, we need to use this kind of arrow, double hit arrow here. We would have something like this. These two bonds remain intact. Nitrogen here, we're now having a double bond with this carbon of the benzene ring, single bond, O negative charge. The other side, no change. But wait a minute, do you see this carbon here? Initially, there was an H atom, we didn't do any change, so there's still an H atom. But the thing is, now it has lost some electrons. In fact, it has lost one. So this carbon here will take a positive charge. Let me just circle the charge for you to see better. Positive charge here, negative charge there. Okay? Which means that this side potentially has a lower electron density than the rest of them. And that's the reason why if I'm going to put an electrophile to a nitrobenzene, it's not going to go to the ortho position. I will show you. Now, this bond here can be pushed to this position. And I can draw another resonance structure. Now, this takes positive because this hydrogen here goes down, hydrogen here, and this pi electrons has moved up. So what you notice that for resonance structure drawing, the pi bond moves over, the positive charge swap position. You see, it jumps alternating. That's how we know you're on the right track. The top part didn't change, negative, dative, and this is your para position. So let's do it one more time. This pi bond on the right side can be pushed down, right? And you get this drawing. Okay, now this carbon takes positive. What do you see now? In the benzene ring of a nitrobenzene, the ortho and the para positions will take some positive charge at some instance, which means to say that any next electrophile that will attack the ring here will want to avoid these positions because electrophile means that they want electron and these carbon position, they are short of electrons. So that explains why they are meta-directing, because comparatively, the meta position at any instant will not gain any positive charge. Now, this part is done. So why is it that this group here, like nitrile group, is deactivating? As you see, when I position the NO2 group next to the benzene ring, we see that at some instance, in fact, most of the time, inside the ring, there is a shortage of electrons. You see that it carries a positive charge, positive, positive. So it pulls electron density away from the ring. And by that, we mean that the ring is having less electron and would not be attacked by an electrophile that easily. So that's why it's deactivating. Now, if you try all these examples here, it works the same way. All these have something in common. They have a polarized pi bond next to the benzene ring. Let me just briefly show you. For an aldehyde, when you draw this out, it's a CO double bond here, H. For a nitrile, it is a CN triple bond. Right. Again, you have a pi bond, polarized pi bond over here. So that means when I push electron density, just in the same manner, you can push it up out of the ring and forming positive charge. And the last one, COR is a ketone. C double bond O R. R is an alkyl group. So likewise, you see a similarity here. This bond is polarized and is conjugated directly to the benzene ring. So now we know that these groups here, of course there's more than that, this list is not exhaustive. These are electron withdrawing groups. They are deactivating, they are meta-directing. The next electrophile we prefer to go to is third position.